the chance to talk about such an interesting topic here. Yes, so these three lectures are a very quick overview of a part of representation theory of real semi-simple Lie groups, namely the tempered representations. I'll go into what they are and why you would want to look at them. And then we'll make a start on classifying them. So this is the plan for today. I'll start with just a general overview of the kind of groups we're looking at and the kind of representations. Then the specific representations that these three lectures are about, the tempered ones. And then make a start on trying to list them all. This is some basic Lie theory on Cartan subgroups and roots. And then the last part of the lecture will be about classifying a part of those representations that we are interested in, the discrete series. Yes. So I always like, I think a nice way to learn maths is to pick a good question that you want to answer, a good question that is interesting in itself and also forces you to learn some interesting maths to answer it. And the question that Bram and I will answer today and tomorrow is what this is. This is an abelian group associated to a group G. And to answer that question, what this thing is, we will have to learn some representation theory and some K-theory and C-star algebras. So Bram's lectures are about C-star algebras, like this symbol here, and K-theory, which is this. And my lectures are about the G, the kind of group that we're looking at, and what you need to know about those groups to compute this thing. All right, so let's start with the general setting. So it's good to make clear what kind of groups we're looking at, and these are the kind of groups. So real semi-simple Lie groups, and to be more specific, connected linear real semi-simple Lie groups. And what does that mean? The linear part means it's a closed subgroup of GL and C for some C. The whole theory applies more broadly than what I'm going to say now, but the class of groups that I'm going to define here is convenient, but still contains enough examples to be interesting. So we're looking at just closed subgroups of GL and C. And the semi-simple part means closed under conjugate transpose and has finite center. So let's look at some examples of groups of that type. There's three classes of groups in this category. There's the compact groups, which are compact as topological spaces, as subsets of GL and C. For example, SONC and SUNC. So these are the n by n real orthogonal matrices with determinant 1, and these are the n by n unitary matrices with determinant 1, compact sets. There's also complex groups, for example, SL and C, the complex matrices with determinant 1. SONC, which is defined by the condition this, just the usual definition of orthogonal matrix, but then for complex entries. And those first two classes of groups are the easiest cases. And the third class of groups is actually the most interesting and the most complicated. And the main part of the lectures will be about this third non-compact, non-complex case. But I'll also mention what simplifies in the compact case and the complex case. So examples of non-compact, non-complex groups in this class are SLNR, so real matrices with determinant 1. And these two, yeah, the P, Q means that they preserve an inner product of this type or a norm of this form. Right, there's a signature P, Q. And so these are the real matrices that preserve this inner product, this norm with determinant 1. And the little 0 here means the connected component of the identity matrix. And these are the same, but for unitary matrices with determinant 1 preserving this. So not unitary, but I mean preserving this norm. Another example is the symplectic group on R2n that preserves the symplectic form on R2n, also non-compact, non-complex. I'll define what complex means in a bit, actually. Here are some non-examples. So ON is not an example because it's not connected. The universal cover of SL2R is not a linear group, doesn't lie in a matrix group, so this is not an example of the kind of group we're looking at. There's the group of upper triangular matrices in SLNR, which is not closed on the conjugate transpose, so not an example. It'll play a role actually in a later lecture, but not the kind of G we're looking at. And GLNC has infinite centers, so it doesn't satisfy this requirement. So the groups SL and R will come back as examples regularly, and particularly SL2R. Is it clear what kind of groups we're looking at? Okay. We'll sometimes be integrating over groups, and we'll use a H measure. And a H measure is a measure dg on the group, which is left invariant. It's a left H measure. And left invariant means if you multiply from the left by some element g prime, the interval stays the same. And there's a unique H measure up to a scalar, and just fix one that is, of course, not 0. The groups G, the semi-simple groups we're looking at, are unimodular, and that means that a left H measure with a G prime here is also a right H measure with the G prime there. So that's an extra property of H measure in this case. Now, the whole, these lectures are about unitary representations, actually just a special class of unitary representations, but that's the whole framework. A unitary representation, G continuous unitary representation, is a homomorphism from G to a unitary group on a Hilbert space. And the notation I'll always use is curly H sub pi will always be the Hilbert space on which representation pi acts. So the fact that it lands in unitary operators is why it's unitary. And continuity means that this map from G times the Hilbert space to the Hilbert space, the natural action map, should be continuous. There's a notion of equivalence of unitary representations, and an equivalence means probably what you might expect. There might be, is there a question in the chat? Oh, is the screen frozen?
At least to me.
Sorry, okay, can people see me changing slides?
Yes, I can see it clearly.
Okay.
I can see it clearly.
Okay, I will reconnect. Thank you.
Okay. So equivalence is what you might expect. We talk about unitary representation. So an equivalence should be a unitary isomorphism between the two Hilbert spaces of the two representations, but it should preserve the representations pi. So for every group element, this relation should hold, and that's what it means for the representations to be equivalent. The unitary representations to be equivalent. This property is called intertwining, by the way. Intertwining operators will come back in the third lecture as well. So if that exists, then we call representations equivalent. And okay, the notation for the equivalence class is not yet surprised. So G hat, G with a hat, is the set of equivalence classes of unitary. Oh, sorry, no, I'm going to say this later. Apologies. So here are some examples and non-examples of unitary representations. The most simple one is a trivial representation, which is a representation in the vector space C, which maps every group element to 1, the identity map on C. And that's a unitary representation because it preserves the natural product on C. Then for a compact group G, what I'm saying here is that unitarity is not really special because you can make any representation unitary by averaging the inner product. So suppose in this case we have a finite dimensional representation, a homomorphism from G to GLNC. On Cn we have the set of inner product, which may or may not be preserved by the group. But if you then define this averaged inner product, which we can do because G is compact, so the integral always converges, this defines an inner product which is preserved by G, and that makes this representation unitary. And this also works for infinite dimensional Hilbert spaces. So the message from this example is that for compact groups, unitarity is not very special. You can always put an invariant in a product on a representation space that you have. Here's a non-example. If you take the natural representation of SL and R on Rn, it doesn't preserve the standard in the product, and because any two norms are equivalent on Rn, it doesn't preserve any in a product on Rn. So that's not a unitary representation. And actually, for the non-compact semi-simple groups, unitary representations, most of them will be infinite dimensional, of course, apart from the trivial representation. Okay, so that's what a unitary representation is. Here is the example, an important example that motivates the notion of template representations that we're going to be looking at. Left and right regular representations. Now the Hilbert space is L2 over G, which is defined with the H measure we chose earlier. And the left and right regular representations are just defined by translating functions from the left and the right, by left and right multiplication. So for the left regular representation by a group element G, it means you plug it in there. And for the right regular representation, you put group element on the right side. Now these are unitary. For the left regular representation, it follows directly because the H measure is left invariant. But as I pointed out, because these groups are unimodular, the H measure is also invariant under the right regular representation, so R is also unitary. And they commute, these two actions commute by associativity. So we can view L2 over G as a unitary representation of the group times itself by L and R. Okay. Now, given a representation, it would be useful to decompose it into irreducibles. Ideally, you want to list a list of smallest building blocks of your unitary representations and then decompose a given representation into those building blocks. When do we call a representation irreducible? It just means it has no non-trivial sub-representations, which means no non-trivial subspaces that are invariant under the group action. So of course, the zero space is invariant under group action, the whole space is invariant under group action, and there can be no other invariant subspaces. And then the representation is called irreducible because it doesn't break up into smaller bits. Here's an example. If we take the left regular representation of G on L2 of G, and we take the subspace, which is often called L2G, well, like this, for example. The invariance under the subspace of L2 of G of functions that are invariant under the right regular representation of some compact group. Compact group which is not trivial, not the whole group G which is compact. And that space, because L and R commute, that space is invariant under the left regular representation, but it's not zero and not everything. So the left regular representation is not an irreducible representation. And that leaves us with the question, can we decompose it into irreducibles? And that's what these lectures are about. And this is the notation that I was thinking of earlier. G with a hat is the set of all equivalence classes of unitary representations. So unitary representations that are irreducible up to the notion of equivalence that I mentioned earlier. This notation will be coming back a lot. Okay. Now I mentioned that given a unitary representation, it's useful to decompose it in a sense into irreducible ones. And the question is, to what extent is that possible? Now, if G is a compact group and we have unitary representation pi, you can always decompose it as a direct sum. And that's the ideal case, direct sum of G invariant subspaces. But when G is not compact, we can't in general decompose a representation as a direct sum. For example, for L2 of G, for example, if the group is the real line, by the way, the real line has infinite center, so it doesn't quite fall into our class of groups, but the theory still applies here. So from Fourier theory, we know that L2 of R, we can get the Fourier transform, and that is a decomposition of a function into these representations of R. But that decomposition is continuous because lambda can vary continuously. So we know that the Fourier transform is a useful decomposition of a function, but it's not discrete. So it's some sort of continuous decomposition. That's what we'll need to do in general. Okay, that leads to the notion of template representations. Are there any questions so far? Feel free to interrupt otherwise. So template representations are motivated by trying to decompose L2 of G, the left and right representations, into irreducibles. So here's some preliminary notation. We can look at this bundle of Hilbert spaces. There's no topology or coherence between the fibers in this definition. So we just take the bundle, which adds an irreducible unitary representation. The fiber is the Hilbert space for pi times the dual space, continuous dual space of the Hilbert space of pi. So we just put them together as fibers of some bundle over G hat. And suppose that we're given a measure mu on the set, we can define this direct integral, which is, by definition, the space of measurable sections, modulo equality almost everywhere, from G hat into this bundle. So that means that so phi of pi lies in H pi tensor H pi dual every pi, and the square integrability means that this integral converges for the given measure mu. Now phi of pi lies in here. This is again the Hilbert space, tensor product of Hilbert spaces. It's actually isomorphic to the Hilbert-Schmidt operators on H pi, so this can also be seen as the Hilbert-Schmidt norm of phi of pi, and that is a space on which G times G acts. So on every for every copy of pi, we have an action by G here via pi, and there's an action here by G also via pi dual. So just to be explicit here, for all psi in H pi dual, G in G and V in H pi, this definition, this dual representation is defined in this way. This was the action here. And this gives a representation of G times G, so in this copy and in this copy. And now the representation looks kind of diagonal in a sense, so it acts on every pi separately. And this turns out to be the best we can do in terms of diagonalizing and decomposing L2 of G as a representation. So that's what this direct integral means, square integral sections of this bundle. Okay, so just like for the Fourier transform on the real line or on the circle, you can define a Fourier transform on a more general group G by this formula. If you have a function on G, I'm taking smooth completely supported functions here. The Fourier transform is a function on the dual space, on G hat. So, so f of f goes from G hat to, well, it's a section of this bundle E. Initially just a section of the bundle E. Oh, I shouldn't actually say this now, sorry. Don't know what's happening with my... yeah, maybe I shouldn't mention it now. So the Fourier transform of f at an element in the dual space is this thing, pi of f. And of course, pi, the argument of pi is a group element, but if we put in a function, it means this. So we average pi of g with this function. And initially, this is a boundary operator on this h of pi. So a priori, it's not yet clear that this is really a section of this bundle E, because those were the Hilbert-Schmidt operators. But it turns out that for our groups and for smooth completely supported functions f, this bounded operator is actually a Hilbert-Schmidt operator. And that means an element of H pi tensor H pi dual. And that means that this F Fourier transform of F is a section of this bundle E. So it lands in H pi tensor H pi star at every pi. And this is a theorem that especially this bit, it's true more generally. There is a unique measure mu on the dual, so that this becomes an isomorphism, so that we can we have a G times G equivariant isomorphism from L2 of G to this space we just defined. And on the right-hand side, as I said earlier, the action by G times G, or I forgot a dual space here. On the right-hand side, the representation by G times G is as diagonal as possible. It acts on every pi separately. So this unitary G times G equivariant isomorphism is the best way we have to decompose L2 of G into irreducible representations. And as we saw for the real line, this may be a continuous representation if this set is not discrete, not countable. And this measure mu is the Planck-Cherel measure. Now, existence and uniqueness of mu is an abstract theory, but computing mu explicitly and computing the support of mu is a very difficult bit of work by Harris-Chandra. And the support of that measure is by definition the set of tempered representations. We'll denote this by G hat with a subscript temp. The representation in there are called tempered. So my convention, by the way, is that the tempered representations are the irreducible ones, are all irreducible. And it's the support of this measure. So if you want to decompose the representation L2 of G, as a G times G representation, the tempered representations are the ones you need. And the goal of these 3 lectures is to say as much as possible about how to classify the tempered representations of G. Harris-Chandra did very important work on semi-simple Lie groups. He classified, he computed the Planck-Cherel measure, which was a monumental bit of work. Included in computing the Planck-Cherel measure is computing its support, or at least the support up to a set of measure 0. And that's what he did in the 1970s, 60s and 70s. Then later, Knapp and Zuckerman classified really all tempered representations. Now, we won't reach the full classification by Knapp and Zuckerman at the end, but I'll say as much as I can about it, but we'll classify almost all tempered representations in any case. And as I said at the start, the goal is to discuss as much as is needed to compute this K theory of the reduced C-star algebra of G.
Peter, there's a question.
Yeah.
In the chat box. What are the assumptions on G such that the Fourier transform exists and becomes an isomorphism?
Yeah, this is true. You don't need to be a Lie group. I'm not 100% sure what the exact measure I can say. Locally compact. Initially, it was done for unimodular groups. I don't know if it needs to be second countable. Yeah, the exact extent to which locally compact unimodular, maybe second countable, something along those lines. A lot of things I'm going to say will be true more generally than what I'm stating.
Thanks.
Yes, okay. So that's the goal for these lectures. Discuss the classification of these tempered representations which are in the support of the Planck-Cherel measure. So, some examples of tempered representations. In the compact case, this is the Peter-Weil theorem. In the compact case, I said earlier that every unitary representation decomposes as a direct sum, including in this case, L2 of G decomposes as a direct sum. We don't need this continuous kind of decomposition. And all the spaces are now finite dimensional. The set G hat is countable. The tempered representations are all of them. So that the support of the Planck-Cherel measure is the whole G hat. G hat is called the unitary dual, by the way. And the Planck-Cherel measure is just the counting measure. So this isomorphism here is the Peter-Weil theorem, which is the special case of this punctual decomposition for compact groups. And again, an example which doesn't quite fit into our class of groups, the circle. The theory, of course, still applies because we know about Fourier transforms on the circle. Then the unitary dual is Z, but the states are parameterized by the integers. And this Fourier transform that I mentioned earlier is really the Fourier transform of periodic functions. And then we get that Fourier transform is a special case. Okay. Another example which doesn't quite fit into the class of groups we're looking at, but which is familiar, which is the real line. Whereas we saw earlier, we can expect some kind of continuous decomposition. Now for the real line, the unitary dual is the real line, again the real line. And the representation corresponding to the real number is this one, the ones that appear in the Fourier transform. Because R is abelian, the tempered dual is again the whole unitary dual. And the Poincare measure is just the big measure on R. And the Fourier transform is now just the Fourier transform as we know it from analysis. So that's again a special case of the Poincare transform. Now, here's a more interesting example from our point of view, which is the example that will keep coming back, which is SL2R. So 2 by 2 matrices with determinant 1. Here is a picture of the whole unitary dual of G. I mentioned the trivial representation, which is always unitary and always irreducible. And then there is more parts. There is a discrete part, like we see for the continuous group case. Now there are pairs of dots. So an infinite, countably infinite set of pairs of dots, which is the discrete series. There are two continuous families of tempered representations, two half lines. For this half line, the bottom is closed, so the bottom point is included. For this half line, the bottom point decomposes into two separate dots. And these are all the tempered representations on this side. The trivial representation is never tempered unless G is compact. And for SL2R, there are additional unitary reducible representations, the complementary series, which are not tempered. And the complementary series is something you have to add in to get all the unitary representations, which is already an indication that finding all the unitary representations, irreducible representations, can be challenging. So at the end of the third lecture, I'll again draw this part of the diagram. And by that time, we'll know why it looks like this. So that the goal of the 3 lectures, at least in the case of SL2R, is to understand why this part of the diagram looks like this. Now we can also write down the Poincare measure. So the Poincare measure is supported on tempered representations by definition. So the Poincare measure here is 0. What does it do on this set here? Now we have two half lines. On the left vertical half line here, if mu is the coordinate along the half line, the Poincare measure is this. Here d mu is the Poincare, is the big measure on the half line, and it's multiplied by a weight function u hyperbolic tangent of pi mu over 2. And on this half line, it's the same, but we have a different weight function here. So it's explicit, but it looks a bit more tricky than the case of the real line. And now there is a mix of continuous and discrete parts. So on the continuous part, we get a function times a back measure. And on the discrete part, every point has positive measure. And the measure in the nth pair of points, each of the 2 points has measure n over 2 pi. Yes. Okay. Now there is a special kind of tempered representation, and that's the kind of representations that this first lecture is about, and that's the discrete series. So we solve for SL2R, there's a continuous part and a discrete part. We solve for compact groups that the decomposition is always completely discrete. So there may be a discrete part, and in addition to possibly a continuous part, and the discrete part is called the discrete series. And the definition is a representation, temporal representation in the discrete series if the single point set pi has positive measure. And that means in this decomposition, it's a direct summand instead of just part of some continuous decomposition. That means we can write the Pancherel decomposition space. I guess we should have had this here for the notation consistency. So this decomposition decomposes as the discrete part, which is the direct sum, and the continuous part, which is this. And outside of the representations, there is nothing because the measure is 0. Now, a group may or may not have a discrete part like this, like we saw R doesn't have a discrete part. So the question is, when does a group have a discrete series? And if it has a discrete series, can we classify the discrete series representations? And this turns out to be useful more broadly, even if a group doesn't have any discrete series representations. We will use discrete series representations of subgroups to classify temporal representations. That will happen in the third lecture. There's an equivalent characterization. A representation is in the discrete series if and only if this matrix coefficient here for some non-zero v and w, a function like this is called a matrix coefficient, if that is square integrable. To be precise, the term is every k finite matrix coefficient is square integrable. And then you can use matrix coefficients to embed h pi into L to the g, so direct summing. Okay, so that's the discrete series. And in this lecture, we're going to classify discrete series representations of G and see when it has any representations in the discrete series. Examples. In the compact case, we saw that G hat is discrete. It equals G hat temp, so the Pancherel measure, the support is all of the dual, and the decomposition is completely discrete, so every unitary reducible representation for a compact group is in a discrete series. In the real line, there was no discrete part of the decomposition, so there was no discrete series for the real line. In the case of SL2R, as you might imagine, the discrete series is this discrete set of points that we saw. The points away from the two half lines, so the 2 points at the bottom of this one half line are not in the discrete series. And for SL and R, if n is at least 3, there are no discrete series representations. So there's a big class of group where they don't exist and sometimes they do exist.
Peter, there's a question.
Yeah.
Does the matrix coefficients for discrete series, are they required to be square integrable modulo the center?
Center is finite in my setting. So it doesn't matter. In all of this, you at least, as I said, the exact assumptions on the group can vary, but you at least want compact center, and then it doesn't matter. Okay, so I'm going to claim that it's good to classify temporal representations. Here are some reasons why that would be interesting. First of all, this representation is an important representation of G times G. We know that the Fourier transform is for example, useful to study differential operators on the real line or on periodic functions. In this case, we can study differential operators on a space like G mod H, where H is a complex subgroup. Also, for example, in hyperbolic geometry, you want to look at spaces like G of this type with 2 quotients from 2 sides, where this is a compact group and this is a discrete group. Then it's useful to know how L2 of G decomposes, so we know how the functions or sections of vector bundles on these kind of spaces decompose. The immediate goal for these 6 lectures by Bram and me is to describe the C-star algebra, as Bram will do at the end of this lecture. And a third reason why it's important to classify temporal representations is you can use them to classify a bigger class of representations, which is the admissible ones. So a little bit about that, just for context. This won't play a role in the rest of the lectures. Classifying the unitary representations, unitary reducible representations of G, is an unsolved problem. It's a very difficult problem that hasn't been solved yet after many, many decades of work. So you can look at have a bigger class of representations, the admissible ones, inside which you can try to look for unitary ones. Now, the technical definition is that an irreducible representation, which is generally not unitary, doesn't have to be unitary, is admissible if, when you have a compact subgroup, there's a maximal compact, so they're not containing any bigger compact subgroups. If you restrict the representation to the maximal compact K, that decomposes as a direct sum of irreducibles, as we saw, and every irreducible should only occur finitely many times. So it's conceivable that if you have a unitary representation of K, you might have the same irreducible occurring infinitely many times, but that's not allowed. And that's the definition of admissible. It turns out that every unitary irreducible representation of G is admissible. So we at least know where to look for them. And Langlands classified all these admissible representations, assuming we know how to classify the template representations. So what he did was, if you know how to classify template representations of certain subgroups, that allows you by an induction procedure that I'm going to talk about later today, to classify all the admissible representations. And if you know all the admissible ones, at least we have some place to look for the unitary irreducible ones, which is what we really are after, but which is a very difficult problem. So here is a diagram to describe this. It's a very general notion of irreducible representations, and that is too wild to work with, it turns out. Inside them, we have the admissible ones, which are more manageable and can classify. Then we have the template ones, which these lectures are about, and inside them we have the discrete ones, which I'm going to talk about today. And between them, we have the unitary ones. So we know how to classify them. If we can classify the discrete series, as I'll explain, we can classify the template representations. If we can classify the template representations, we can classify the admissible ones, as Langlands showed. And then at that stage, we have a place to look for unitary representations. And that's then a problem which at least you have, at least you know where to look. Okay. This is just some context which doesn't play a role in the rest of the lectures, just a motivation. Okay. So in the rest of this lecture, I'm going to talk about classifying discrete series representations. I need some background information first about Python subgroups and root systems. First, quick crash course on Lie algebras. If we have our group G, which lies in GLNC, this is true for any closed subgroup of GLNC, we can define the exponential map by this Taylor series expression, which turns out to converge. And the Lie algebra of G is a vector space, which is the tangent space to G at the identity element, because G is a manifold. But you can describe it in this way: it's all the n by n matrices, such that all these matrices lie in G, in T and R. On the Lie algebra, we have some additional structure. We have the adjoint action by the group, which is by conjugation. And we have the adjoint action by Lie algebra on itself, which is by commutators, commutator bracket. And it turns out a lot of information about a connected Lie group is contained in its Lie algebra. Some notions: subalgebra over Lie algebra is a linear subspace which is closed under this bracket structure on the commutators. An algebra is called commutative if the bracket is 0, which you might expect from this definition. And I mentioned the notion of a complex Lie group earlier. Complex means that this Lie algebra is a complex subspace of N of C. Okay. Now, just some examples of Lie algebras. The Lie algebra of SLNR or SLNC consists of the matrices with trace 0. And that's because the determinant of the exponential of the matrix is the exponential of the trace. And here the Lie algebra of the unitary group. Again, the unitary group doesn't fit into our framework because it has infinite center, but we can still talk about it. Is the anti-self-adjoint matrices. So the star stands for conjugate transpose. And the Lie algebra of SUN is the intersection of this one and this one for the complex numbers. And that consists of the matrices which are both in U of n and in SL and C. So the traceless anti-permission matrices. Okay. Now, a Cartan subgroup plays an important role in a lot of structure theory of Lie algebras. It's a maximal commutative subalgebra, often called H, so that the adjoint operators, so they're taking the bracket, taking commutator with X. This is a commutative subalgebra, so we have a bunch of commuting operators on G and want them to diagonalize simultaneously. Then it's a Cartan. And then if you have a Cartan subalgebra, a Cartan subgroup is a centralizer of that subalgebra in G. So all the group elements in G, the matrices in G that commute with all the elements in H. There's finally many conjugacy classes. So what's important is the conjugacy classes of Cartan subgroups. There's finally many. And they all have the same dimension. And the dimension of a Cartan subgroup is the rank of the group. Now, I would say the reason why the compact and complex cases are easier than the third case is that for a compact or a complex Lie group, there's only one conjugacy class of Cartan subgroups. And that really simplifies things a lot. So the interesting bit of the theory is how to handle different Cartan subgroups, different conjugacy classes of Cartan subgroups. If you have a Cartan subgroup, by assumption, all these adjoint operators diagonalize, and the eigenspaces are the root spaces. So what that means is this precisely: for a given alpha, a real linear functional from H into complex numbers, this space, GC alpha, consists of the matrices in G tensor with the complex numbers, so that for all y in H, so this thing here, of course, this is the same thing as add y x. All these operators add of y have these eigenvalues, depending on y. So it's the joint eigenspaces of all those adjoint operators. G tensor C is G plus IG, and the Lie bracket is extended complex in this complexification. And a root means an alpha for which this is not the zero space, and the alpha can't be zero either. So the set of roots R of H comma G are the linear functionals on H into the complex numbers, for which the non-zero linear functionals, for which this space is not zero. So for which there is this joint eigenspace. And then it follows from just decomposing this eigenvector theory that the complexification of G decomposes as the complexification of the Cartan, which corresponds to alpha 0, which is not by definition of a root, plus all these eigenspaces. And this structure of the complexification of G plays a big role in all of Lie theory. So some examples. SL2R. For SL2R, there are two conjugacy classes of Cartan subgroups, a compact one and non-Cartan. I will start with, I'm just turning off my email. So a compact Cartan of SL2R is SO2, and the Lie algebra is spanned by this matrix. So we know that for it should be the traceless anti-symmetric matrices which is spanned by this. Now there are two roots. This is a one-dimensional space. It's a one-dimensional space spanned by this matrix. And the root alpha is defined by mapping this matrix Y1 to 2i. And then the roots system is plus and minus alpha. Turns out that if you have a root, then alpha minus alpha is always a root as well. And now the root spaces are these two one-dimensional complex subspaces of G tensor C. So this is just a matrix computation. If you compute Y1 commutator with this one, you get 2i times this matrix. And here you get the same thing with minus 2i. And then we have a root space decomposition. The complexification of SL2R is SL2C. And it decomposes a three-dimensional complex subspace, complex space of matrices, decomposes as the complexification of the carton, so C times this matrix Y1, and then the two root spaces. Now, there's also a non-compact carton corresponding to a different conjugacy class, and that's the diagonal subspace. So these are all matrices in SL2R, and this is also it is commutative, and it's a carton. Now, the Lie algebra is spanned by this matrix, and traceless. And now the root system again consists of two roots, plus and minus, giving root beta. And now the root beta is real valued. So the root beta is defined by mapping this to 2. And again, now the root space is a little bit simpler. The root space for beta is just matrices with just an element in the top right being non-zero. And for minus beta, it's non-zero elements in the bottom left. And again, we have this root space decomposition, the carton, plus the positive root space, plus the negative root space. All right. Any questions so far? Okay. If not, then I'll move on to the last part of this lecture, which is the classification of the discrete series of a semi-simple group G. Okay. First, when does it exist? Well, I think there's a question in the chat. All right, so for the, thanks Roger, for the Plancherel theorem, a separable, locally compact, liminal topological group. Then you have the Plancherel theorem. Thanks. Okay, so a result by Harris-Chandra is that a semi-simple group G has discrete series representations if and only if it has a compact carton subgroup. Let's look at some examples. If the group G was already compact, then of course a carton is a closed subgroup, which is also compact, namely a maximal torus. Compact an abelian subgroup of G which does not contain any bigger abelian subgroup. So for compact groups, there are always discrete series representations. Well, we know this because the decomposition of L2 of G is then discrete. For SL2R, we just saw that we have the compact carton SO2, so that's why SL2R has discrete series representations. For SUPQ, there is a compact carton subgroup on the diagonal, isomorphic to this many copies of the circle. For SOPQ, the connected component of SOPQ, in the case where PQ is even, there is a compact carton, which is again a copy of circles. Of course, every compact carton is a copy of circles. If P and Q are both odd, this is not big enough to be maximal abelian. But for P or Q even, SOPQ has the compact carton and therefore the discrete series. In the complex case, there is never a discrete series because if you have a carton subgroup of a complex Lie group, it turns out that the Lie algebra of the carton is always isomorphic to Cn, and via the exponential map, H is isomorphic to this group, the non-zero complex numbers to the n, which can never be compact. So complex Lie groups never have discrete series representations. Okay. To classify the discrete series, we need the notion of analytic integrality, which is this. I'm defining this for elements for real linear functionals on a compact carton, in the Lie algebra of a compact carton with imaginary values in this case. It's analytically integral if when you pair it with an element of the kernel of the exponential map, so we have x t going from t to t. If on the kernel, it maps into 2 pi I times integers. And the set of elements that do this are noticed by lambda. Now, this is just another way of describing the unitary dual of t, because if you because analytic integrality exactly means that this representation of T is well defined. So for this xi, we want to define homomorphism e to the xi from T to the circle by this formula. E to the xi of the exponential of some element is this thing. And this, of course, means that if x of x is trivial, we want the right-hand side to be trivial, which means that this thing has to be in 2 pi I times z. So that's another way of defining analytic integrality. It just means that it gives a representation, unitary representation. It's just an implicit example. If you have Rn, and E1 up to En is a standard basis of Rn, and with superscripts we mean the dual basis of the dual of Rn. If the torus T is Rn mod Zn, then the exponential map is the quotient map, kernel is Z to the N, and now the integral elements are the Z span of 2 pi I times all these dual things. So it's, in particular, it's a countable set. It's a lattice inside this vector space. So it's countable. Okay, now a bit more background information for the classification. The while group for a, you can say the while group of a root system, or you can say the while group of the group G and this compact Cartan, is the normalizer. This is the we'll come back later as well. Normalizer of the torus inside G, mod the torus, and it turns out the normalizer lies in. I haven't defined K here yet. K is a maximal compact subgroup, so it turns out this is always compact. Maybe you can forget about this for now. But the normalizer in G equals the normalizer inside a maximal compact subgroup. And it acts on roots, that's why we can call it the while group of the root system. It acts on this vector space by the adjoint action, by the dual of the adjoint action, and permutes all the roots. And it's a finite group, by the way, that's important. Okay, now the thing we fix an inner product on this vector space, which is invariant on the action by this while group. It's a finite group, so we can do this. Now, if we have an element in this dual space for which the inner product with all roots is non-zero, then we can pick out half of the roots by the requirement that the inner product with this xi that we fix is positive. And so we have, say, a root system, say, for example, this root system. You pick some element xi, which which is not orthogonal to any of the roots. Then you pick the ones which have positive inner product with that xi, and in this case, it's these 3 roots. So it's a way to pick out half of the roots which lie on one side of a hyperplane. And it depends on the choice, this xi. And we call them the positive roots. And then some notation we use is that a row element, the letter rho, always means half the sum of some set of positive roots. So I'll denote by rho xi half the sum of these positive roots that I just defined. And we'll also use rho xi, which is a compact analog, which is half the sum of the positive roots for which the root space lies inside a maximal compact subgroup. So here we've okay. So to make it more concrete, K is G intersected with UN inside GL and C. So it's a compact subgroup which is maximally compact, doesn't not contain any bigger compact group. So some roots may have this property and some don't. And so we take a sum over a subset of the positive roots, called the compact roots, for which these eigenspaces lie in the complexification of the maximum compact. Then the classification is this. So we have to assume that G has a compact Cartan, otherwise it doesn't have a discrete series. Then the statement for now is not so, it's a bit vacuous, but I'll give it more structure in a minute. For every lambda in, so imaginary value linear functional on Lie algebra T, there is a discrete series representation. We first have to pick lambdas that have 0 in the product with all the roots. Then the lambda defines a positive root system. And if we add this row term to lambda, this has to be n-th multiple. And so this is a discrete set, countable set. Now, just the statement for all lambda, the additional pi lambda is a bit vacuous because I'm not really saying what the correspondence is. I'll say that in the next few slides to make it a bit less trivial. But, okay, so given the correspondence, every discrete series representation occurs in this way, and that leaves the question when are two of them isomorphic, equivalent. And that's the case if and only if this finite group, so the action by this finite group W tells you when two of them are equivalent. So then we really know what all the discrete series representations are and which one are equivalent and which one aren't. Now, okay. To finish this, I need to say what the relation between lambda and pi lambda is. I'll do this in two steps. First for compact G and then for non-compact G. For compact G, if we have a irreducible representation pi, the notion I'm going to use is highest weight. We can define, we can generalize the notion of a root. If you have imaginary value linear functional on T, then the corresponding weight space, the T weight space, is this thing. So for every x in this parton, the action by the pi action on the new weight space is defined by this. So we have a joint diagonalization of all these commuting operators pi of x. And pi of x is, so pi is a homomorphism from G into unitary operators on some vector space. And pi of x is the derivative Laplace instance. So again, joint diagonalization. And for mu, for which this is not the zero space, we call mu a T weight. And that allows us to define the correspondence between lambda and pi lambda in the compact case. The characterization now of the discrete series pi lambda is that the highest weight is lambda minus rho lambda. So that means, highest weight means the dimension of this weight space is 1, and every other weight of pi lambda, every other T weight, can be obtained from this highest weight by subtracting, so m alpha here is greater or equal to 0, by subtracting positive integer, non-negative integer linear combinations of the positive roots. So highest in the sense that the positive root direction is up. So that's the correspondence for compact groups, the highest weight of pi lambda given by this. Now for non-compact G, we define it in terms of compact subgroups. So K, as I said, was G intersected with UN, maximal compact subgroup. Now, the characterization of pi lambda, the property that defines the correspondence, that the lowest K type of pi lambda is this. And what does that mean? The lowest K type means we restrict pi lambda to K. So pi lambda is a homomorphism from G into a unitary group, and we can restrict this to the subgroup K. And then we have representation of K. And then we can try to, we can decompose that representation of K into irreducible representations of the group K. And in that decomposition, the highest weights that occur, the highest weight as defined on the previous slide in compact case, are of this form. So we have this lowest K type, highest weight, and now we add non-negative integer linear combination of the positive roots, and that gives you all the highest weights. So again, the positive roots are the up direction. In that sense, lambda, this is the lowest K type. Now, in the rest of these lectures, it's only important to remember that the discrete series can be classified, and these exact conditions will not literally come back in this form. But I just wanted to say what the correspondence is between lambda and pi lambda. And this is what it is for the compact and non-compact cases. Now, just to finish up, I want to do the SL2R case. For the compact cation subgroup SO2, because we need to start the compact cation subgroup, the is represented by this. Alpha, so we parameterize IT star by the real numbers, by taking A of alpha over 2 as a basis. Alpha maps y1 to 2i, so it maps this to I times t. We just take an inner product on the real numbers, we just take this one. Then the inner product of lambda with the roots alpha, it's not if it's the inner product is non-zero with alpha, because then the minus alpha is automatic. The inner product is now non-zero if and only if t is non-zero. And then for positive t, the positive roots are alpha, and half the sum of the positive roots is alpha over 2. For negative t, the positive roots is just a set minus alpha, and then this is half the sum of the positive roots. Okay, now the exponential of this y1 is this element of SO2. The kernel is 2 pi z times y1, because then this is 0. For this same lambda as we had before, supposing t is positive, then rho lambda was alpha over 2. So lambda plus rho lambda is t plus 1 times alpha over 2. And this is the integral if and only if this pairing with the kernel of the exponential map was in 2 pi I z. And this pairing equals 2 pi I times t plus 1. By the way, all of these things are, if you work through them yourself, you see what's happening. If you see somebody else doing all the algebra, you need to, doing this, working through this yourself is the best way to see what's going on, but just saying what the result is. So now integrality means t is integral. Also positive, so t is a non-zero natural number. And for that t equals n, so for that natural number, we have what's called the holomorphic discrete series of SL2R, which is denoted by Dn plus. So that's one of the 2 points in every pair of points that we saw in the diagram earlier. And then for negative t, we get, in the same way, we get t is minus natural number. And then for traditional reasons, this discrete series representation is noted by Dn minus, and it's called the anti-homomorphic discrete series. So the 2 points we saw, the pairs of points are always a Dn plus and Dn minus. So that's what the theory looks like for SL2R, and the Y group now is trivial because the maximal compact is SO2, which is equal to the torus, so this normalizer is just T itself, and therefore there are no equivalences between those discrete series representations, so they're all inequivalent. Okay, time is kind of up, maybe I won't go into this very deeply. Here's an explicit form for these discrete series representations in the explicit space. So you can write down the space and an action and you get the discrete series. Let's get the anti-homomorphic ones as well. And that's the end of the lecture. So what we've seen is the template representations of G are the ones that occur in the Punchinelli composition of L2 of G. If there's a compact carton, we have a discrete subset, and we can classify discrete series representations as I saw. And that's what we need to remember for the next few lectures. All right, that's it for today.
I thank you, Peter. What's the etiquette here? Do we applaud or
Sorry?
do we applaud or what's the etiquette here for lectures?
I don't think you need to applaud for that.
Right. Any questions to Peter? There is a question.
Well, there's a question, but I don't know the answer to. The question is about analogies between locally pro-finite groups. I don't know what that means, so I can't answer the question. But periodic groups, and periodic groups are what Anne-Marie is going to discuss on Wednesday to Friday. And I don't know the answer to this question, but we will probably see some analogs and differences between the real and periodic cases in Anne-Marie's lectures.
Yes, indeed. Anne-Marie is going to point out some analogies and differences indeed. So we'll have to wait until Wednesday for that. All right. Any other questions?
Well, maybe I take the opportunity to jump in because of some things I'm going to say. But Peter, you didn't discuss so far any topology on G hat, right?
Yeah, that's right. It's
Yeah.
all measure theoretic. Yeah.
Yeah.
The topology is not needed in a strict sense. When you discuss, when we'll see the reduced system algebra, we'll see that there is a topology, and the non-Hausdorff points correspond exactly to non-commutativity in C-star algebra. That's interesting from non-commutative geometry point of view, but I haven't mentioned it because we strictly speaking only need the measure theory for now.
Yeah. So I will introduce some topology in my first lecture, but there are different descriptions of it, and I will not elaborate on it too much either. But I mean, you can describe the topology completely representation theoretically, right?
Right. It's uniform convergence on compact sets of matrix coefficients. So if you can approximate the matrix coefficients of representation by matrix coefficients of different sort of functions on G, if you can approximate them by matrix coefficients of a sequence of other representations uniformly on compact sets, then it's in the closure.
Yeah.
And that's the felt topology.
Yes. Yeah, indeed. So I will not give this description, but algebraic description of the whole thing. But I thought it would be good to bring this up, that there's different ways to describe this topology. We will see in due course.
There's a question about the G-equivariant differential operators and temporal distributions. There is a lot to say about them. I'm not really sure how to answer this question, but it's a very broad area. I guess maybe one possible answer is that in Hochs lectures, CBC will talk about Dirac operators, and they're equivariant differential operators that are used in representation theory, index theory. And that's just one example of the kind of G-equivariant differential operators that occur. And you also mentioned temporal distributions. So it's also the case. Okay. There's a lot you can say about this, but temporal representations. So one thing you could say is that if you have a space of this form, V is a representation of K, or maybe not even irreducible. This is something like the L2 sections of an associated vector bundle over G mod K. And if we know temporal representations and we know the Poincaré formula, we can decompose this as so then we can give an explicit decomposition of this space in terms of representation theory, and we know how G acts, namely G acts here. And that, yeah, if you can decompose the space that the operator acts on, that helps you study its kernel spectrum, etc. It's a very broad thing. So maybe maybe the most complete answer is that Hango probably mentioned something about these differential operators in her lectures. Another question: if F is K finite for SL2, how many discrete series components would appear in the Poincaré inversion? So F, try to understand the question. So F is a function, F is an L2 of SL2R. And K finite means if you let the maximal compact SL2 act on F, the space that spans K finite. What do you mean by the Cauchy inversion? Or do you mean the Fourier transform? Okay. You don't necessarily get all. No, you don't get all the discrete series representation. So if you know something about the K transformation behavior of F, it will end up in. We have this. If you know something about, say, for example, the right K transformation behavior, we're in a subspace of this, just like we're here, and then, well, it's related to this actually, and then this space may be 0 or non-zero, so only the pi for which this space is non-zero will contribute, and that is not all the pi's in general or all the discrete series. I don't know if that's an answer to the question.
Would it be finitely many? Depending on
Sorry?
finitely many, perhaps, depending on the K type of the vector, test vector.
Sorry, I have trouble understanding what you said.
I was thinking perhaps depending on this K type of this transformation property of this F, we could have to only appear in maybe finite many discrete series.
A given K type appears in finite many discrete series. That's right, because the yeah, that's right. So if F transforms, in this case, transforms according to a given K type, you will only see finite many discrete series representation. So that may be the best answer. Yes.
Well, many questions. Good. Clarifying the. Okay, you're doing a great job actually reading the questions, so you don't need me. Okay, go ahead, please.
This is Roger's question, the wild group for SL2. So this is for the compact carton. So this is the case for SL2R and for the compact carton is very special because the maximal compact K is abelian. So K is now SO2. So it's equal to the carton subgroup. And that means that because K is equal to T, that means that this is equal to NT over T. The non-large of T in itself is T, so we just get T over T, which is a trivial group. Is that the answer? And this is also a reason why you don't see everything happening for SL2R, because K is an abelian group, so it doesn't really. There's no
surely the Weil group for SL2R is the two-element group. The two-element group.
This Weil group for the compact isn't. For the non-compact carton, I will actually mention this in the third lecture. So if you have this is just so the Weil group you need in the classification of the discrete series is the Weil group of K. So I'm really talking about the Weil group of K here, and in this case K is abelian, so it doesn't have a Weil group. But we'll need other Weil groups as well later, and they will be we'll see one that is the two-element group as well.
Okay, thank you. Yeah.